Okay, so just to review what pH and pOH are, we've already looked at this a little bit so far. So a high pH means you have a relatively low hydronium concentration. So remember that hydronium really is inversely related to pH. So meaning the higher the hydronium concentration, the higher the hydronium concentration is, the lower the pH will be, which means the stronger the acid is. And then just to overview, remember that each change in a pH number is actually a times 10 increment. So if I have something that is a pH of 10 in comparison to something that's a pH of 8, I would say that the pH of 10 is 100 times more basic. So it would be like times 10 and then times 10 again. So, and that's because it's based on a logarithmic scale. So we're going to review what strong acids and bases are. But essentially, a strong acid is something that will 100% ionize. So not necessarily 100%, but technically 99% plus. And the reason for that is because strong acids don't have equilibrium. So in order to be claiming that something is strong, that means you must have it to completion. So when you're doing calculations with strong acid and base equilibriums or any sort of calculations, you are assuming that all of the reactant becomes product. So you are not doing any ice table or anything like that. You're actually just using stoichiometry to determine concentrations, and you'll see what I mean in some of the examples we're doing. So this is just a visualization to show you. So a strong acid, so this is representing the acid before it donates the proton, so while it's still together. So let's say this is something like a HCl, or if it's hydrobromic acid, like a HBr. So the A is just representing the anion. So what happens is if you were to graph out what it would look like as products, so remember these are the products after the ionization happens, you'll see that there is pretty much zero reactant left over. And that's because it's more than 99% done, so meaning it's not in equilibrium, it's pretty much considered to be all product. Okay, so before I get into this next example, I want to just go over what our strong acids are. Let's see how. Okay, so strong acids, there's only 6 of them. If it's not a strong acid, if it's not one of these 6, then it is automatically assumed to be weak. Okay, so we have hydrochloric acid, we have hydrobromic acid. Hydrochloric is correct, but apparently hydrobromic, there's a typo there. But anyways, nitric acid, and then we have hydroiodic acid, then we have sulfuric acid, and, oops, I'm out of the frame here. I'll have to make this font. Anyways, I'll have to add a new text box. And perchloric acid. Oh boy, my skills are not great right now. Okay, so we have 1, 2, 3, 4, 5, 6. So those are the 6 strong acids. If it's not one of these, it's automatically assumed to be weak. Okay, so just be careful. One that is a common weak acid that gets confused with a strong acid is actually hydrofluoric. It's because all of the other halogens, so chlorine, bromine, and iodine, are strong, but actually hydrofluoric acid is in equilibrium, so it is considered to be weak.